So the aim of this video is to understand and prove the Leibniz rule in differential calculus. So the Leibniz rule is a generalization of the product rule, so we'll begin by writing out the product rule and then we'll see what idea is going to give rise to the Leibniz rule, or what question is going to give rise to the Leibniz rule. So firstly, the product rule then. So the product rule says that if you want to differentiate the product of two functions, so we've got two functions, f of x and g of x, and we might, at some points in the video, drop writing the of x. We might just write this f and g, where we know that f and g are both functions of x, just because it's simpler. So the product rule says that this is the derivative of f of x, which I might just now write f prime without the of x bit, times g undifferentiated plus the other way around, where you don't differentiate f and then you differentiate g. So that's the product rule of differentiation. The question that gives rise to the Leibniz rule is, what is the second derivative of a product? And then what is the third derivative of a product? And then what is the fourth derivative of a product? What is the nth derivative of the product? So this is the question. What is the nth derivative dn dxn of this product, f of g? Can we write down a general formula for what that is equal to? And it turns out you can, and that formula is what's called the Leibniz rule. So firstly, let's try and do this. Let's try and derive it first, get the intuition behind why the formula is true, and then we'll formally prove it by induction. So to get some intuition, let's just look at some concrete examples. So the next one up is going to be the second derivative. So let's think about what the second derivative of this product is going to be equal to. Well, that's just going to be the derivative of the thing that we've worked out with the product rule, which is f prime g plus f g prime. So we now want to differentiate this. Well, this is just the sum of two products, so we just need to differentiate this and add it to the derivative of this. And we're going to differentiate each of these things by applying the product rule again. So let's do this. So we'll make some more space. So we'll go over here. So the derivative of this then, so it's going to be this thing differentiated times this undifferentiated plus this thing undifferentiated times this thing differentiated. So that will give f double prime g plus f prime g prime. So I hope you can see why that's the derivative of that. Just applying the product rule to this, where you now view f prime as the new f. And then likewise to the second bit, so there'll be f prime, the first thing differentiated, times the second thing undifferentiated, which is g prime, and then plus the first thing undifferentiated times the second thing differentiated, which will then be g double prime. And now we can see that these are the same thing, so overall this is equal to f double prime g plus 2 f prime g prime plus f g double prime. So that's the second derivative of the product of f of g. And we can see how it's sort of starting to look like some nice pattern that we might have seen before in maths, but we haven't gone far enough to come to that conclusion yet. So let's now do the third derivative of the product. So the third derivative of f times g. So it's going to be the derivative of this thing. I won't write that out. The derivative of this thing, the way we're going to do it is by differentiating each of these and adding them together. And the way we're going to differentiate each of these is with the product rule. So the first one will be f triple prime g plus f double prime g prime. So this term comes from differentiating this, not differentiating this. And this second term comes from not differentiating this and differentiating this. And then similarly with the other terms. So we've got a 2 that we mustn't forget now. So the 2 must stay. And then we're going to get 2f double prime g prime plus 2 f prime g double prime. So because the 2 doesn't affect the differentiation, the constant can be pulled out the front. Plus then the final thing will be f prime g double prime plus f g triple prime. And now loads of these are the same thing. So you can see this is the same thing as this, and this one here is the same thing as this. So overall, rewriting this gives f triple prime g plus 3f, whoops, double prime g plus 3 f single prime g double prime plus f g triple prime. And hopefully you can now start to see the pattern that these coefficients in front of each of these are actually the binomial coefficients. So they're what you would get if you expanded something, and I'll just make some more space. It's difficult writing at the bottom of the board part on this iPad. So if you look at things like x plus y to the power of n, when you have x plus y to the power of 1, this is just x plus y. When you look at x plus y to the power of 2, this is then equal to x squared plus 2xy plus y squared. Then when you look at x plus y to the power of 3, it's then equal to x cubed plus 3x squared y plus 3xy squared plus y cubed. And you can see that actually things are very much so analogous in these derivatives. This one is analogous to this. This one is analogous to this. This one is analogous to this, and it's because these coefficients that are going to sit in front of these are going to be the same coefficients that you see here, and we'll think about why that's going to be. So actually, when you want to take the nth derivative, we can see that we're going to end up with these sums where there is every possible combination of how you can distribute the differentiation. So you've got to differentiate 3 times. This is the one where you've differentiated f 3 times and differentiated g none. This is the one where you've differentiated f 2 times and, oh, we've made a mistake there, dropped a prime, should be g prime. This is the one where you've differentiated f twice and g once. This is where you've differentiated f once and g twice, and this is the final extreme where you differentiate g all 3 times and differentiate f 0 times. So we have this sum of every possible way that you can distribute the differentiation amongst f and g. And then the coefficients in front of here are going to be the binomial coefficients. And why is that? It's exactly the same reason as the coefficients here are the binomial coefficients. It's because when you want to distribute things amongst the f and the g, it's just like the way you distribute amongst the x and the y here. When you're expanding them, you've got this great big sum. Here's where you just pick x 3 times from the brackets. Here's where you pick x twice and then y once. Here's where you pick x once, y twice. It's exactly the same. And then these coefficients are then how many different ways there are of doing this in different orders. So in this case, because you pick f 3 times, there's only one way you can do that. But when you pick f twice and g once, there's 3 ways that you can do that, because you could pick the g first and then pick the f and the f second, or you could pick the f first, g in the middle, and then an f, or you could pick f, f, g. There's 3 different orders in which you could perform the differentiation, just like in here where there are 3 different orders of how you could pick the x and the y, because from each of the brackets you have to pick either x and y. So let's write down what we intuitively think the formula is going to be then for the nth derivative. So our speculation is that the nth derivative of this product, i.e. the Leibniz rule, is going to be the sum from r is equal to 0 to n, and then we want each possible amount that you can differentiate the f, so f to the power of r, or not to the power of, rather, differentiated r times, and then g will be differentiated what's left, so it will be differentiated n minus r times. So as we go from r is equal to 0, this will be the case where you differentiate f no times, and in this case you'll have n minus 0, so you'll differentiate g the entire n times. When r is equal to 1, that will be f prime here, so you'll have differentiated f once, and this will be n minus 1, so the other n minus 1 differentiations will have gone to the g, and so on, all the way up to r is equal to n, which will be where you've differentiated f the full n times, and then you'll have n minus n, which is 0, so g will be not differentiated at all. So this will give all the possible ways that you can distribute the differentiation among the f and the g, and then you're going to have the binomial coefficients here, so n choose r, which I write like so, but equally validly, you could write n, c, r, like so. And this is n factorial over n minus r factorial, r factorial. And remember, this has a huge number of different meanings. It's a very powerful concept in maths. But the reason that it's relevant here is it tells you if you have two things, so let's say we have just the letters A and B, and you have n lots in total. So just to give a concrete example, let's say we have n is equal to 5, and if, let's say, 3 of them were A's and 2 of them were B's, so we've got these things here, then 5 choose 3, or 5 factorial over 2 factorial, 3 factorial. This tells you the number of ways that you can rearrange these 5 things, where all of the A's are considered equivalent and all of the B's are considered equivalent. So, for instance, if I were to swap these two A's round, I'd just get back the same thing, and that's not counted as a separate combination in this calculation. Whereas, if I swap one of the A's and the B's around, so if I look instead at A, B, that would be counted as a separate combination here. So this tells you all of the different ways that you can rearrange these things where 3 of them are the same and 2 of them are the same. So for instance, just to give you another example, B, B, A, that would be a different combination. B, A would be another combination. B, A. So there's loads of them. The total number of them is going to be given by this, 5 choose 3. And equivalently, if we change the number, so let's say we now have 7 in total, and 1 of them is an A and 6 of them are B's, equivalently 7 choose 6, which is equal to 7 choose 1. The formula gives the exact same thing. That's the total number of ways, total number of different combinations in that case. So if we just scroll down. So the case where you have one A and all the rest are B's. This is a much simpler problem. You can see that it's 7 in that case, that it just depends on where you put the A, this position, this position, this position, this position, this position, and there's 7 total possibilities. It's a more complicated question when you've got more than one, when each of them is not 1 or 0. 0 would be the even simpler solution. If they were all B's, there's only one different combination. But 1 is also very simple. So why, I would just like to talk a little bit about why this tells you how many different ways there are of ordering these things. And that's an incredibly interesting question, beautiful question. So let's think about it. So if we had 5 separate letters, so A, B, C, D, and E, and we wanted to know how many different ways are there of ordering these, it's a much simpler problem because they're all different. So because we've got 5 separate things, there are 5 different things that we could put in position 1, and then for each of those possible things that we put in position 1, there's then 4 different things that we could put in position 2, and then for all of those 2 combinations of things that we could put in the first 2 positions, there's then 3 different things that you could put in position 3, and then 2 different things you could put in position 1, and the final one is then fixed. So the total number of different ways of reordering them is then 5 times 4 times 3 times 2 times 1, some huge number, which is 5 factorial. Not that huge, so it's 6 times 4, 24 times 5 is 120. So there's 120 different ways. You could write them all down if you had a lot of time, all the different reorderings of this, and you'd find that it's 125 factorial. Now when we want to make things equivalent, when we want to say now this B and this C, we're going to make all of those the same letter. We're going to turn them all to A's, and this D and this E, we're going to make them the same letter. We're going to make them B's. How do you work out how many fewer reorderings there are in that situation? Well, let's start off just with one of them. So let's imagine firstly turning these 3 into the same thing. So they're all going to become A's. and then we'll leave the final two as separate. And we want to work out how many fewer reorderings are there now that all of these three are equivalent. Well, what you can imagine is having a great big set, and these are horrific braces that I've just drawn here, but never mind. You can have a great big set of all these different original combinations in the original problem. So I'll just draw a few of them. So here are a few of them, but there's all 120 of them in here. And what we can now imagine doing is partitioning this set up into bits that are all now going to be equivalence classes in the formal language of set theory. So we can imagine chopping it up into things that are all going to be equivalent now that these things at the front are all made the same. So in fact, all of the ones that I've put in there are all going to be in an equivalence class together. And they're not going to be the only ones in that equivalence class. There's going to be other ones as well. And the reason is all of these three have now been made equivalent. So all of these different things that were different originally are now no longer different. They're all equivalent now that we've made all of these the same. And there'll be things that are outside of this equivalence class. So for instance, this one, D, A, B, C, E, that's not in the same equivalence class. That's different. Making these three things all the same still leaves that different to these. You can see if you made all of these A, all of these three would be made exactly the same thing, but they wouldn't be made the same thing as this if A, B, and C have all become A. So this is an example of an element that's in a different equivalence class. But this one has a bunch of things that are equivalent to it. So D, B, A, C, E is equivalent to it. D, A, C, B, E would be equivalent to it. So all of those would be in an equivalence class together with other things as well. And what we can now ask is how many things are going to be in each of these equivalence classes? And the answer is going to be that each of the equivalence classes is going to be the same size, and we can very easily work out what it's going to be. So we can do that by just considering this concrete example of this one. Let's work out all of the different things that are going to be in this equivalence class. So we've got 3 already. So we want to look at the other ones. So let's work them out. So we've got A, B, C. We've swapped the B and the A here. Then we've swapped we've done a sort of rotation there. Let's do a few more. So we could swap A and C. That one would also be equivalent. Then those are the two with A in the front position. So let's have the ones now with B in the front position. We've got BAC, so let's have BCA, DE. And then all the ones with C in the first position, we've got CAB, so then we need CBA, DE. So those are the ones that would be also in there, that equivalence class. So all of these are going to be made equivalent in our new problem where all of these, the A, B, and the C, have all been made the same letter. Because as you can see, when they're made the same letter, they're all just going to be exactly the same thing. So we can see that that's 6, which is 3 factorial. And the reason that it's equal to that is it's the number of different ways of reordering these 3 things that have all been made equivalent to one another. And the number of ways of reordering them is 3 times 2 times 1, i.e. 3 factorial. I hope that was obvious when I was actually working this out. You know, I went through every single thing that had A in the first position, every single combination with B in the first position, every single thing with C in the first position, and for each of those there's 2 possible options of what's in the second position. In this case it's B and C, in this case it's C and A, in this case it's B and A, and then for the final thing there's only 1 option. So each of the equivalence classes is going to have the number of ways of reordering the things that have all been made equivalent to one another, which in this case, because it's 3 of them, it's going to be 3 factorial. If we'd made 4 of them all equivalent to one another, it would be 4 factorial. If we'd made 2 of them equivalent, it would just be 2 factorial. So each of these equivalence classes is going to contain 3 factorial things that are all going to be made equivalent to one another in this new problem where these 3 letters have been made the same thing. And you could see exactly the same for this one here. So the D and the E are going to stay put, but then we just need to rearrange these 3 things in all of the different ways, which is 6 different ways. So there's 3 more that we could add in here, and that will make that complete equivalence class. And then there'll be loads of other equivalence classes where the D and the E are in different positions yet again. So if we had, for instance, A, D, B, C, E, that would be in a totally different equivalence class. A, B, D, E, C, that would be in yet another totally different equivalence class with 6 things in it. So these would be truly, this one example from this equivalence class and one example from this equivalence class, those would be truly different elements in our new problem. So what we now want to know is how many total different equivalence classes are there, because those are the things that are truly separate in this new problem. So you just need to take 120 and divide it by the total number of things in each equivalence class. So you've got 5 factorial divided by 3 factorial. And that's how many different ways there are of rearranging in this new problem where these 3 things are the same. So it's 5 factorial over 3 factorial, which will just be 5 times 4 is the total different number of ways of reordering that. Now we're doing a slightly different thing because we're now setting these 2 final things equal to one another. So what you can imagine doing, we're going to do this whole thing of splitting it into equivalence classes again. So you can imagine the set of all the different combinations that were truly different combinations in this problem. So all of these different combinations. So I'll write a few in. So we've got this one, AADE, so that's the one that corresponds to this equivalence class here. Let's do the one that corresponds to this equivalence class. That would be not what I'm about to write down. So it would be D, A, E. That would be represented by this equivalence class of 6 things. Then this next one along would be A, D, A, E. So that's that one here. And then this final one, it would be A, D, E, A. So there's going to be 20 things in... Oops, sorry, I didn't mean to do that. There's going to be 20 things in total in this new set of all the possible combinations in this problem. And now what we want to do again is partition it up into things that are going to be equivalent. Now that we're making these final 2 things, the D and the E, equal to one another, we can imagine to make it the same as our original problem, we're renaming them both B. So of these examples, are any now going to be equivalent? No, I don't think any are. This has somehow gone wrong. There should be an A on the end there. I'll just add that in. So none of these are actually going to be equivalent. But, for instance, this thing, AAED, that's a different combination in this problem. And those 2 at the top there are now going to be equivalent. And these equivalence classes are only going to contain 2 things because there's only 2 different ways of reordering these 2 things that have been made equivalent. So we're going to have to divide again by 2 factorial to find the total number of things in this new problem, which is how to rearrange, how many different ways are there of rearranging that. So it's going to be 5 factorial over 3 factorial, 2 factorial, which is 5 choose 3. Or equivalently 5 choose 2. So back to the problem of the Leibniz rule. So here we are. So the nth derivative of the product of f of g, we've already established that it's going to be made up of this sum of all the ways of distributing the differentiation. And then why is the coefficient going to be equal to this? Well, the intuition, and we are going to do a proper proof of this rule, don't worry, but the intuition for why it's equal to that is because when you're doing these calculations, these repetitive uses of the product rule, you're going to get each of these possible different ways of distributing the differentiation. And how many times are you going to get it appearing? It's going to be basically every different thing that can happen is going to happen at some point in this calculation. So it's going to have every possible way of ordering the derivatives that you've got. So I don't feel like I'm explaining that particularly well, so let me draw some or write something down to help. So if we take a specific example, so we'll take the example of, let's say the 4th derivative. So we're going to take the 4th derivative. In fact, we'll do the 3rd derivative since we've actually calculated that one. So we'll do the third derivative of f of g, or rather f times g, not f of g, that's different. So we know that this is going to be made up of these sums. One of the terms is going to be where you've differentiated f 3 times and you've differentiated g once. One of the terms is going to be f differentiated twice and g differentiated once. One of the terms is going to be f differentiated once, g twice, and one is going to be this. So in the case of this one, and indeed in the case of this one, there's only one order in which you can do that differentiation. You differentiated f, you differentiate f again, and then you differentiate f again. In this one, likewise, you differentiate g, and you differentiate g. In these two, however, it's more complicated because if you want to end up with that, it might have been the case that you differentiated f, and then you differentiated g. Or it might have been the case that you differentiated f, you differentiated g, and you differentiated f again. Or it might have been the case that you differentiated g first, then you differentiated f 3 times. And in this calculation, this repeated differentiation, every one of those possible combinations is going to happen somewhere in that calculation. So this case, where you've differentiated g once, that's the case where, and it was the first thing to be differentiated, that's the case where you had this, you went to this bit in the product rule, and then subsequent to that, it's where you've differentiated the f twice, so it goes to this bit, where the f got differentiated, not this bit again, and then again it will go to, it's complicated because we've accumulated them into the same term with the 2 here. If we hadn't put the 2 there, it would have actually made this more obvious how it's going if we'd written it out separately and then written them out separately here. So really this should be written as this plus another one of these, and then it will be the equivalent, this term here in this one over here. So in that calculation where you're repeatedly performing the product rule, every single one of these combinations is going to come up somewhere, so they're all going to end up being summed together. And of course, because they're the same thing overall that you get, the outcome, they're all going to be put together into one term. So overall, you're going to have these 3 separate ones of them. And likewise for this, you could have differentiated the f first and then g twice, or you could have differentiated g first and then f in the middle and then g finally, or you could have differentiated g first, g second, and then f finally. Those are the 3 different ways that you could get to overall this answer, this having one of these terms. And in that calculation of doing the derivative, every single one of those is going to be an option somewhere. So they're all going to end up in a great big sum. So when you collect them all together, you will get the coefficient 3. For the general nth case, where you're considering, or the rth case rather, where you're considering f differentiated r times and g differentiated m minus r times, what we want to know is how many different ways then are there of reordering how they've been differentiated. So for instance, you could have differentiated f r times and then differentiated the g's n minus r times to produce this result. But every possible reordering of those is also another way that you would get this. And the thing that I haven't proven to you, which you have to have the intuition of, is that every single one of those different reorderings of how you've performed the differentiation is going to happen in that calculation. That's the bit that you have to have intuition for, and that's hopefully the intuition that you've sort of got by us doing these concrete examples. And don't worry, we are going to formally prove the Leibniz formula using a proof by induction, so you don't have to rely on the belief in that intuition, but hopefully you do have that intuition that every single possible one of these reorderings is going to be something that's going to appear at some point in that repetitive application of the product rule. So all we need to do then to know the coefficient that's going to be in front of this term is just know how many ways are there of reordering this, and that's what we've just discussed. That's going to be n choose r, or equivalently n choose n minus r, but that's not so pretty, so we put in the n choose r. So that's why these binomial coefficients appear here. So that formula there, that is the Leibniz rule, so we could put a box around that. And I hope you understand the understanding that I've tried to give you there for why this is true. That's the intuitive derivation, if you like, of where the Leibniz rule comes from. What we're now going to do is formally prove it by proof by induction, because as you can see, some of the arguments that we've used there, they're quite tricky to understand, and can you really argue that that will work all the way up for whatever n? And I suppose you can, but the intuition's a little bit loose. So we will now formally prove that this formula is true. So let's perform a formal proof by induction of this formula then now. So we will need some more space. So we'll go over here. So we'll write the formula out again. So the nth derivative of the product f times g is equal to the sum from r is equal to 0 to n of n choose r times f differentiated r times g differentiated the remaining number of times n minus r times. So for a proof by induction, we need to prove it in the base case, i.e. we need to prove that it holds true for 0, and then we assume it's true for some n is equal to k, and we then want to prove that it's true for n is equal to k plus 1. And then actually an axiom of logic, known as the axiom of induction, tells us that then it's going to be true. The intuition for why the axiom of induction is true is that if it's true for the base case of n is equal to 0, then we know then it's true for n is equal to 1, because we've proven if it's true for n is equal to k, it's true for k plus 1. Then because it's true for n is equal to 1, it's then true for n is equal to 2, and n is equal to 2 gives that it's true for n is equal to 3, and so on. And the axiom of induction tells us that it's a valid, reasonable argument to then say it's true for absolutely every single natural number. It's just a word, it's just a fancy axiom for how our common sense logic works. So let's prove then that it's true in the case that n is equal to 0, the base case. So that means differentiating no times. So the answer should be f times g. So looking at the right hand side now, we've got the sum from r is equal to 0 to 0 of n choose r, f r, g, n minus r. So there's only one term in here. It's going to be 0 choose 0 times f differentiated no times g differentiated 0 minus 0 times, which is still no times. And 0 choose 0 is just 0 factorial over 0 factorial, 0 factorial, and 0 factorial is 1. So that gives that it's equal to f times g. 0 factorial is just equal to 1 by definition. So next step of the proof is to assume that it's true for n is equal to k, and we want to prove that it's true for n is equal to k plus 1. So to differentiate then the product k plus 1 times, what we can do is that we know that the formula is true for n is equal to k, so we can just put in the formula for the derivative kth times and then just differentiate that again. So this is just going to be equal to the derivative of then the formula for n is equal to k. So from r is equal to 0 to k of k choose r, f r, g, k minus r. And now this is a finite sum here. It might look complicated, but it is just the sum of a bunch of things, and it does end. It's not an infinite sum. So the derivative of a sum is just the sum of the derivative of each of the bits. So this is going to be the sum from r is equal to 0, k, and then k choose r is just a constant, so that gets pulled out. And then it's going to be the derivative of this product f, r, g, k minus r, where of course f and g are both functions of x. So to differentiate that then, we're going to apply the product rule one final time. So this is going to become the sum from r is equal to 0 to k of k choose r, and then the derivative of that is going to be, so f differentiated r plus 1 times, so we've differentiated the first thing, and then it's going to be g differentiated k minus r times, so we haven't differentiated g at all, and then plus the other option, which is to differentiate the g another time, so we'll have f differentiated r times, and then g differentiated k minus r plus 1 times. And now what we need to somehow do is show that this can be rewritten as the sum from r is equal to 0 to k plus 1 of k plus 1 choose r, f differentiated r times, g differentiated k plus 1 minus r times. We need to somehow rearrange this and show that it's equivalent to that. So let's start by splitting this into two separate sums. It actually becomes easier that way, and then we'll combine them back together later on. So we'll split it into this bit and this bit. So this is going to become the sum from r is equal to 0 to k of k choose r, f of r plus 1, g differentiated k minus r times, and then plus the sum from r is equal to 0 to k of, again, k choose r, f differentiated r times, g, and we could rewrite this as k plus 1 minus r, and that's helpful because remember the final form we're trying to get to looks very much so like this. We wanted g differentiated k plus 1 minus r times, so there's our first little manipulation. So we can do this because each of these is just a finite sum, so you can rearrange the terms like this in finite arithmetic with no problems at all, so that's fine. So now comes the time for something clever. So we're going to start by doing something clever to this one. So we're going from r is equal to 0 to k, but actually when we look at this, we're taking the derivative of f of r plus 1, and we would like, remember what we're trying to get to, we're trying to get a formula where f is to the power, f is differentiated r times, not r plus 1 times. So we actually just want to change the index here because the terms we've got here, we have f differentiated 1 times, which is when r is equal to 0, 0 plus 1 is 1, and it runs all the way up to r is equal to k, and at r is equal to k, f is going to be differentiated k plus 1 times. So we're going to re-index the sum. We're going to go from r is equal to 1 now to k plus 1. And now all we're going to have to do is change things a little bit. So in this first thing, we're going to have k choose r minus 1, because now for each of these new indexes, which is 1 greater than the equivalent index here, we don't want to put its new value into there, we want to put its old value. So we're going to need to subtract 1. So for instance, when r is equal to 1 in this sum, you subtract 1 from it to get 0, which is the correct answer for over here. When r is equal to 2 here, that corresponds to r is equal to 1 here. So in this bit, you need to take away 1 to make it the same thing as here. But the reason I've done this is because now f is just differentiated r times, and also g is now going to be differentiated k minus, and now it's going to be r minus 1 there, times. But you can see that those minuses are going to cancel to make a plus, and this is then going to become k plus 1 minus r, which is another nice thing that we want there. So this is going well. Then with this thing, is there anything further that we need to do here? There's nothing further that we need to do for this at the moment, so we'll just leave that one. So plus this same thing, and I'll write it out just to make sure that I don't make mistakes later on. So k choose r, f differentiated r times g differentiated k plus 1 minus r times. So now more manipulation over here then. So this is going to become just g differentiated k plus 1 minus r times. And now what we want to do, actually, it's a very short manipulation, because now what we want to do is put these back together. The problem is the indexes are wrong. So this one runs from r is equal to 0 to k. This one is running from r is equal to 1 to k plus 1. So the way we're going to combine these together is by taking one thing out of this and taking one thing out of this. So taking r is equal to 0 out of this one and taking r is equal to k plus 1 out of this one, because then both will run from r is equal to 1 to k and we'll be able to combine them together. So that's what we're going to do next. So I'll bring this into the center. So this is going to be equal to, so take k plus 1 out of this one. So that will be k choose k plus 1 minus 1. So k choose k, which is just 1. And then f will be differentiated k plus 1 times. G will be differentiated k plus 1 minus k plus 1 times. So g will be differentiated no times. So actually that highest term when r is equal to k plus 1 is just equal to this. So it's that plus then the sum from r is equal to 1 to not k plus 1, which I was about to write, but k. And then of k choose r minus 1, f differentiated r times g differentiated k plus 1 minus r times. And then it's going to be plus, let's take out the bottommost term, the r is equal to 0 of term here. So it's going to be k choose 0, which is just 1. F differentiated 0 times g differentiated k plus 1 minus 0 times, which is just g differentiated k plus 1 times. So it's going to be plus f g k plus 1. And you can see that the two terms that we pulled out are then the most extreme terms of the differentiation. They're the terms where f has been differentiated all k plus 1 times and g no times, and where f has been differentiated no times and g has been differentiated k plus 1 times. And then it's going to be plus the sum from r is equal to 1 to k of k choose r, and I apologise for the siren, I can't do anything about that, f differentiated r times g differentiated k plus 1 minus r times. I lie, I could close the window, but I like the fresh air. So we're going to combine these two together now because they run over the same indexes, so we can do that. So we've got, and I think actually we'll do a bit of reordering. So we'll put this term here because I want things in the right order. So we'll put this term over here because it's f differentiated 0 times. So it should be at this side. And then we'll have the big sum in the middle, and then we'll finally have this one over here. So it'll be the sum from r is equal to 1 to k of k choose r minus 1. And now we want to factor out the f differentiated r times and the g differentiated k plus 1 minus r times, because those are common to both of them. So we're combining them back together. We're grouping the terms that have the same r, so we can write it as a sum of this plus this, and then we're factoring out this bit. So it'll be k choose r minus 1 plus k choose r, those like that, and then f differentiated r times g differentiated k plus 1 minus r times, and then after the great big sum, so this isn't part of the sum, well it is part of the overall sum, but it's not part of this thing, so plus then this final term, which is the final extreme, which is f differentiated k plus 1 times and g differentiated 0 times. Now, we're going to use something called Pascal's rule. So this thing, these chooses, there's a name for this. We're going to use Pascal's rule, which says that if you, and I'll actually use the same symbol, so if you want k plus 1 choose r, it's equal to k choose r plus k choose r minus 1. And this is actually the rule that makes Pascal's triangle work, and the reason that Pascal's triangle, the numbers in it, are the binomial coefficients. But the reason for this, the derivation of Pascal's rule, is simple. You can work this out simply, algebraically, by writing out what these are in terms of factorials. So you can prove it very simply like that. However, there's actually a nicer explanation, a combinatorics explanation for why this is true, which is the way I remember it far more easily than the algebra. So a bit more combinatorics, because the combinatorics is really the star of the show here. I'm just trying to figure out which way I want to go. In fact, we'll just go down. So why is this rule true? Well, you need to understand the other meaning of choose. So we've talked about this, the fact that it means the number of ways that you can reorder these things, where you've got n things in total, and r of them are one thing, and the other n minus r are the other thing. But there's another major meaning for what choose means, and in fact it's the reason it's called choose. So if you have a set of things, distinct things, and you can consider them just the numbers from 1 to n, and you want to make a smaller set which is going to have size r, so you're going to pick r things. So for an example, we could again take 5 choose 3, and there we'd be considering this initial set of things that we're choosing from to have 5 elements, so 1, 2, 3, 4, 5, and then we're going to create a set that contains just 3 elements by picking elements out of this set. So you could pick, for instance, 1, 4, and 5. That would be an option. And then if you ask how many different subsets can you create of this set of 5 things where you're picking 3, the answer is 5 choose 3, because of course in set theory, order doesn't matter. So it doesn't matter if you pick 1 first and then, not 3, 1 first and then 5 second and then 4 third. That's still the same set. So we're not interested in the order, we're just interested in what elements you overall pick. And the answer as to how many different possible combinations you can pick is given by 5 choose 3, or more generally, if you've got a set of n things and you're picking r things, the total number of different sets you can create is n choose r. And again, the reason for that is very simple. If you first imagine picking things and the order does matter, so in this case 1, 4, 5 is going to be different to 1, 5, 4, then if you've got r slots to fill, and in this case r was equal to 3, but more generally, I've drawn 5 here, which is a bit confusing, but more generally this is r. If you've got r things to fill, then there is n possible things that could go in the first slot. There is then n minus 1 possible things for the second slot, n minus 2 things for the third slot, all the way down to n minus r minus 1 things in the rth slot. So that's going to be n factorial over n minus r factorial, because n factorial would continue on all the way down to 1, but if you divide it by n minus r factorial, it gets rid of everything lower than that. So this product, which is the total number of different things that you could create if order mattered, would be that. Now you just want to get rid of the fact that order matters. Well, all you need to think about is how many different ways are there of reordering all of these different things. So, for instance, in this case where we had 5 things and we were choosing 3, in the case that order matters, 1, 4, 5, 1, 5, 4, you'd then have 4, 1, 5, you'd have 4, 5, 1, you'd have 5, 1, 4, and 5, 4, 1. If we were looking at the case where order matters, all of these would be separate, but now in the case that order doesn't matter, all of them are going to be made equivalent, so you then just need to think about how many things are there going to be in each of these equivalence classes. Well, it's going to be the total number of ways of reordering the 3 things that you've chosen, which is just 3 times 2 times 1, which is 6 factorial, these number here. So to get rid of the fact that order matters, you just need to divide through by r factorial, and then you get the expression for n choose r. And that's the reason that that expression tells you the number of ways of picking r things out of n things if the order that you pick them doesn't matter and you're only looking at the final are things that you get, not the order that you picked them in. So why is this helpful for understanding why Pascal's rule is true? Because if you consider this problem here of k plus 1 choose r, that means consider a set of k plus 1 things, so 1 all the way up to k plus 1, and then you want to know how many different ways are there, how many different subsets are there that you can create of this, where the subsets have to have size r, i.e. how many different combinations of r things can you choose from this? Well, you can split the problem up into two. You can say, let's split this element k plus 1 off from the rest of them. Every subset that you create of r things is either going to contain k plus 1 or it's not going to contain k plus 1. So this number, whatever it is, k plus 1 choose r, which is the number of ways of picking, the number of subsets that you can create of r things from this set of k plus 1 things, it's going to equal the number of sets that contain k plus 1, number of sets with k plus 1, plus the total number of possible sets that you could create without k plus 1. So if you can work out these two things, the total number of possible sets that you could create of r things from this that don't have k plus 1, and the total number of sets you could create from this that do contain k plus 1, and you're clearly assuming that k plus 1 is bigger than r, so that this, if r was equal to k plus 1, then there's only obviously one option of a set that you can create and this argument fails. But if we're taking, for example, the example where k plus 1 was equal to 10 and r was equal to 3, then this is clearly going to hold. So we're assuming these numbers are such that you can create a set without k plus 1. If r was equal to k plus 1, then obviously you wouldn't be able to create a set without k plus 1. If you've got to choose k plus 1 things from k plus 1, then you can't do it in a way that doesn't include k plus 1. But as long as k plus 1 is bigger than r, strictly bigger than r, then this will be true. So let's just think about what these two things are going to be equal to. So sets with k plus 1, so k plus 1 is going to be an element, and then you need to select the other r minus 1 elements from what's left. Now there are k things left, you've got to select r minus 1. The total number of ways of doing that is then k choose r minus 1, where order doesn't matter because our whole problem had the premise that order didn't matter. And then sets without k plus 1, so in this case you're not going to have that element, and you need to select all r elements from what's left. So it's going to be k choose r, which is the number of ways of taking r things from the set of k things. So that's why this is true. Very beautiful combinatoric argument, and that's much easier to remember than the algebraic manipulation that shows you that this is true. But you can also do it by the algebraic manipulation, and it's not a difficult algebraic manipulation at all. So what this means we can now do is replace this with k plus 1 choose r. So let's find some space and do that. I'm trying to think where's best to go. So we'll go here, we'll try and squeeze it in here. So it's going to be fg k plus 1 plus, we've then got the sum from r is equal to 1 of 2k of k plus 1 choose r, f differentiated r times g differentiated k plus 1 minus r times, and then plus finally the other one, which is f differentiated k plus 1 times g differentiated 0 times. Now, this looks almost identical to what we were trying to get, i.e. the formula, the Leibniz rule for k plus 1. The problem is that this term and this term aren't inside there. But I claim we can actually add these in, because if we make this r is equal to 0, then the term will be k plus 1 choose 0, which is just 1, f differentiated 0 times g differentiated k plus 1 minus 0 times, which will be this term here. And if we put in r is equal to k plus 1, then it'll be k plus 1 choose k plus 1, which is 1. F differentiated k plus 1 times g differentiated k plus 1 minus k plus 1 times, which is 0 times, which will be this term. So actually we can swallow these two terms into this sum by just extending the indices so that they run from r is equal to 0 to k plus 1. So this is equal to r is equal to 0 to k plus 1. K plus 1, choose r. F differentiated r times g differentiated k plus 1 minus r times. So there we have it. We have proven that if the formula is true for some n is equal to k, then it is also true for n is equal to k plus 1, and therefore, since we've established that it is true for n is equal to 0, it will then be true for n is equal to 1, and since it's true for n is equal to 1, it will then be true for n is equal to 2, and so on. And a deep axiom of logic, the axiom of induction, says that it is then valid, it's a valid logical argument to say that it will be true for every natural number, which of course is our common sense logic. But can you prove common sense logic? No. At some point you have to axiomatize it, so that's what the axiom of induction says for us. So indeed, yes, we can now write for all little n is an element of the natural numbers, this holds true. That is the Leibniz rule. So we'll end the video there. Thank you for watching, and I hope you've enjoyed it.